Hi, my name is Alana Hudson, and welcome to my Lab 2 Motion of a Falling Object video presentation. So to begin, introduction about the lab. The lab is about Newton's second law observing a motion in the real world, specifically a non-zero net force. We did it using Tracker to plot an observed motion and VPython to predict a motion with a specified net force. So either the net force was equal to just the weight force or the weight force plus drag force. We'll be discussing these two forces in the next slide. The tools I used were Tracker and GlowScript. We used a ball of standard size printer paper as well as a phone camera to record the motion. The results were that the computational model that factored in drag force and weight force gave me a more accurate position prediction than just the weight force. And the significance of this lab is that there are multiple forces acting on all objects in the universe, and using weight and drag as a way to predict this motion will have a more accurate prediction. The fundamental principles used in this lab were Newton's second law, which we're very much familiar with at this point, using the velocity and the position equations that you see, but newly gravity and drag. So weight force, in this case gravity, is equal to negative mg times f, and drag force equals to negative b, magnitude of velocity squared times f. You can see more about this in the picture on the far right, which talks about the force of gravity on one object to another, which will be applied to the slab. For tracker analysis, we observed the motion of a paper ball, and I positioned the axis at the center of the ball, and this ultimately created a position versus time graph. As you can see in this video, I dropped the ball, and it corresponds to the graph that you see on the far right. And the main takeaway from this is that the graph produced a nonlinear line, so we know forces are present. The net force does not equal zero, and the ball is not moving at a constant velocity. The measurements and observations collected during this was that the mass of the paper was 0.0045 kilograms, and the observations included the start time, which equals to 0, the initial velocity and position, which both equaled 0, assuming the ball began at rest and at the origin, and the end time was 0.0075 seconds. So for the GlowScript analysis, we'll begin with the no drag as a factor. And as you can see, the initials were all created, the ball beginning at rest and at the origin, so the position and velocity being 0, as well as gravity being 9.8 and j hat being 0.10. As you can see in the turquoise box, we began with solving for the net force equaling the weight force. The weight force in this case was negative ball mass times g times j hat, and we use this to update the ball dot velocity and ball dot position. The graph and the picture of what happened in this computational model is on the far right. If you compare it to the last slide, the difference between this one and that is that we used a constant called B in deciding the drag force. So in this case, W is the same, but FD in this case is the drag force, and it is negative B, the constant that we decided on, times the ball velocity times the magnitude of the ball velocity squared. This W plus this drag force equal the net force in this case, and we also use this to update the ball dot velocity and ball dot position, which you can see resulted in the graph in the picture on the far right. When we compare all three of these, we plot the observed tracker data and the two computational data sets from VPython, the tracker being in orange, the no drag being in purple, and the drag being in turquoise. From this, we can see the computational data that factored in the drag was more like the observed data. This makes sense because the ball of paper was actually experiencing air resistance, in this case drag, and the model without drag did not factor this in, which is why it's so far off from the observed. In conclusion, we observed a ball of paper in motion. We modeled that with Tracker and GlowScript, and we compared all the data. Some error could have been in human error, such as recording the tracker data, and this has to be kept in mind. Does any of the models predict a terminal velocity? I believe that the computational model that factored in drag would definitely predict a terminal velocity. When the object reaches a terminal velocity, the net force of the object and the change in velocity is 0. And for the net force to be zero, the drag force has to be equal to the weight force, which is in the opposite direction. And this can be somewhat seen in the computational model that factored in the drag force. Imagine the object was initially thrown downward, the terminal velocity would be reached a lot more quicker than if it had been dropped from rest. And this would be the difference. Thank you so much.